Okay, so here we're doing another example of rectilinear motion. We have a particle is moving in a straight line, and we are given that its acceleration function is a of t equal to cos of t minus sine of t, and we know also its initial position is going to be 3 centimeters, and its initial velocity is going to be 1 centimeter. Okay, so we want to make sure we get all the information out of the question, and then think about what we're actually looking for. In A, we're going to be looking for the displacement on the interval from 0 to pi. So we know for displacement, all that we're going to look at doing is integrating our velocity function from, in this case, 0 to pi. However, that's a little bit of a problem because we don't know the velocity function. Instead, we have been given the acceleration function. So the first thing we'll have to do is find the velocity function. Let's take a look. For part A, we know that the displacement is going to be the integral velocity from 0 to pi. So let's find v of t. We know that the velocity is going to be equal to the integral of acceleration plus c. And we also know that our acceleration function is given by cos of t minus sine of t. So that's going to be integral of cos of t minus sine of t. So we end up getting that our velocity is going to be antiderivative of cos will be positive sine. Antiderivative of negative sine will be positive cos. We put in our plus c, and now we want to know exactly what the velocity function is going to be, so we're going to find c. Okay, now how do we go about finding c? So think about that for a moment. Think about the information that we are given. We would like to find the c given which piece of information. So you can pause the video here, think about it. How do you find the constant in our velocity function given some of this information? All right, so here, coming back, what we're going to do is we're going to use the fact that we know the initial velocity. The initial velocity is 1 centimeter per second. So here we're going to use the fact that v of 0 is equal to 1 centimeter per second. And actually, this should remind you very much of what we did with separable differential equations. What this is it's an initial condition for our differential equation. So we're going to now use that to solve c, and that shouldn't take too long. Really, we plug in t equal to 0, and we have that our velocity should be equal to 1. So we have 1 is equal to sine of 0 plus cos of 0 plus c. Well, we know sine of 0 is going to be 0, cos of 0 is going to be 1, so we end up with c just being equal to 0. Okay, so really what we have is that the velocity function is exactly equal to sine of t plus cos of t. And because that is our velocity function, we're going to use that to find the displacement. So our displacement will be the antiderivative of sine of t plus cos of t integrated with respect to t, and we're going to integrate from 0 to pi. So let's use FDC2. We end up getting antiderivative of sine is just going to be negative cos. Antiderivative of cos is going to be positive sine. and we're going to be evaluating this from 0 to pi. So we can plug everything in. We get negative cos of pi plus sine of pi. Let's make that a bit nicer. And we're going to subtract from that what we get when we plug in 0. So that's negative cos of 0 plus sine of 0. So what do we end up with? We have cos of pi. Okay, so actually all of this whole thing together is going to be the negative from right here. And we know that cos of pi is going to be minus 1, so that whole thing will be just positive 1. And then we have sine of pi. Okay, sine of pi is just going to be 0. We have here, this will be negative cos of 0, which will be equal to negative 1. And then sine of 0, that's just going to be 0 again. Okay, so we have 1 from the start plus 0. Then we have minus 1 plus 0. So we end up with 1 plus 1. Really, we're going to get that our displacement is equal to 2, and our units are centimeters. So that's our displacement from 0 to pi seconds. Now let's take a look at part B. So part B is to find the distance traveled, okay, during the time period from 0 to pi. So we know distance rather than displacement. Distance is going to be now the integral, not of just the velocity function, but it's actually going to be absolute value of the velocity function. Again, from 0 to pi. And so we need to look at our velocity function and figure out when our velocity function is going to be positive and when our velocity function is going to be negative. So similar to the last one, what we're going to do is we're going to solve when is our velocity function equal to 0. So really that is solving when sine of t plus cos of t is 0. So in other words, we want to know when sine of t is going to be equal to negative cos of t. And that means that t is going to be equal to 3 pi over 4. Again, we're only interested here in the angle between 0 and pi. So t is equal to 3 pi over 4. We're looking at seconds. So that means our function potentially changes from positive to negative, or from negative to positive at 3 pi over 4. Okay, let's set up a table of values again and plug in a test value. So what happens from 0 to 3 pi over 4, and what happens from 3 pi over 4 until pi? Let's take a test value. The first test value we can take here is t equal to, let's say, pi over 4. For the second one, we could choose something like pi or 5 pi over 6. And then let's plug those in. If you plug those into your function, again, you're plugging them into here, your velocity function, sine of t plus cos of t. And if you do, you'll end up getting that at pi over 4, it's positive, and at 5 pi over 6, it's going to be negative. So our function goes from being positive to negative at t equal to 3 pi over 4. And what that means is that when we do our distance and we evaluate that integral of the absolute value of velocity, we're going to have to split it up again into two different integrals. One is going to be positive, but the second one we're going to have to subtract. We're going to have to subtract the area from 3 pi over 4 to pi, and we're going to have to add in the area from 0 to 3 pi over 4. So here we're integrating sine of t plus cos of t dt, and the same for the second one. So now let's go actually use FTC2 and figure out what we get. So here, looking at the first integral, we know our antiderivative. It's going to be cos of t negative plus sine of t. And we're going to evaluate all of that from 0 to 3 pi over 4. We have the same antiderivative for the second one, okay, except it's going to be subtracted, so it's negative cos of t plus sine of t, and that's going to be from 3 pi over 4 to pi. So plug everything in. We end up getting negative cos of 3 pi over 4 plus sine of 3 pi over 4 minus the same thing with 0 plugged in. So it'll be minus cos of 0 plus sine of 0. And then this is going to be continued on the next line. So we have now minus, and we have minus cos of pi. So we're plugging this pi into our function to finish off there with FTC2. So that's minus cos of pi plus sine of pi minus what we get when we plug in our 3 pi over 4. So that's going to be minus cos of 3 pi over 4 plus sine of 3 pi over 4. And let's close all our brackets and let's see what we get with this. So let's just go through some of these values. We have this value is going to be root 2 over 2. We have this one as well will be root 2 over 2. We have cos of 0 with the negative actually will be negative 1, but we have sine of 0 will be 0. Here with the negative, this will all be just positive 1. Sine of pi, however, will be 0. Then we have negative cos of 3 pi over 4 again. That's going to give us positive root 2 over 2. And again, sine of 3 pi over 4 is also going to be root 2 over 2. So now let's just put this all together. We end up with root 2 over 2 plus root 2 over 2 from this first part. Then we have minus 1 plus 0 from this second part. Then we have minus 1 plus 0 minus from here, bracket root 2 over 2 plus root 2 over 2. And then we want to put all of this together. And if we do so, we end up with root 2 from here plus 1 from here. And then we have minus 1 from here, so they'll actually cancel each other out nicely. And then this will be over here a double negative, so we're going to have plus another root 2. So it's going to be plus root 2, and this whole thing together will just give us 2 times root 2, and this is our distance traveled. This is going to be centimeters. And so for this one, that is our distance traveled. Now, there was a part C here. So we found the displacement, we found the distance traveled, but now we're looking here at part C. We want to find the function s of t that models the position of the particle at time t in seconds. So again, we're going to have to go back to the information that was given to us. Okay, we started off with acceleration, but we used that to find velocity. Okay, and we did that using the fact that we knew the initial velocity here was 1 centimeter per second. So I want you to think for a moment, how can we use what we have and what we found to find now the position function s of t. So pause the video, think about it. Okay, so we know s of t can be defined in terms of the velocity. So let's take a look at how that works. For part C, we know that here s of t is going to be the antiderivative of velocity. We'll have to find that constant c, and so we can use our velocity function, which is sine of t plus cos of t. We can plug that in. We get here sine of t plus cos of t. We do our antiderivative. Antiderivative of cos will be negative, antiderivative of sine, rather, will be negative cos. Antiderivative of cos will be positive sine. And so this is what our position function looks like, but we need to figure out what this constant is going to be. So here, just to differentiate from what we were doing before, let's call this constant C2 rather than just C. Now we want to find C2. So we're going to find C2 using, for this one, our initial displacement. So we were given that the initial displacement, s of 0, was going to be equal to 3 centimeters. And so we can plug that in. We get 3 is going to be equal to negative cos of 0 plus sine of 0 plus C2. Let's fix that up. Plus C2, which means very much that C2, if this is 0, and cos of 0 is 1, so all of this is going to be minus 1. Bring that to the other side, we get that C2 is going to be 3 plus 1. C2 is going to be 4. So now we know our displacement function, s of t, will be exactly negative cos of t plus sine of t plus 4, and that will be our position function in centimeters. And so that's the end of this last example for rectilinear motion.